maybe I'll take this. Hi. How many of you watched Storage Wars? Almost nobody. It's pretty cool. They open a storage locker that got seized because you forgot to pay your bill or something like that, and then you look at it, and then you get to pay to bid on it, and then you start taking stuff out of the storage locker and figure out what's in it. And sometimes you find, a $1 million painting or some other mostly useless stuff. So I think it's quite similar to the databases and storage stories that I'm gonna tell. It's gonna be a real life drama, and I'm not affiliated with ANU, which makes the show. So it's gonna be almost as cool, I promise. All right. So the Art Genome Project is something that's about 6 years old. It's very simply put. It's you can see it as Pandora for fine art. However, it's also quite different from that. So we basically take experts, art historians, and they classify works of art. So a classification is these individual features are called genes. So an example of a gene can be something very simple, like this is a landscape, or this is a portrait, something like that. So it acts as a tag. Genes, however, have values, and they range from 0 to 100. And so more complex genes are things like contemporary participation or feminism, for example. So these are usually art movements. These are things you can find in literature about art. I don't recommend reading a lot of art speak. It's very thick and complicated. But these are terms that come again and again in literature about art written by art historians. And a team of art historians creates this genome, this kind of classification system for works of art. So one way of understanding these values is if you look at a work of art, let's say an Andy Warhol's pop art, we would say it's an iconic work of pop art, and it would have a value of 100 under the pop art gene. And the Roy Lichtenstein will be not quite as iconic work of pop art and would have a 75 in the value of that gene. So we go by hand and add these values for every single work of art, and we have close to many hundreds of thousands of those today. It's the largest database of contemporary art online. So you do this data by hand, and then the idea was to recreate a search engine, a discovery mechanism on top of that data. And actually what's interesting, it just replicates what happens in the real world when you go to a museum or a show, or when it's a group of different artists. A curator has picked maybe a central theme or a central work, and then has put next to this work other works by other artists that are similar to that. So we tried to build a similarity engine 6 years ago on top of this data. And this data is an evolving set. So it started with about 200 genes, and today it's about 1,200 genes. So think of this as a 1,200 gene, 1,200 feature and dimensional problem. So that's cool. So here's my gene and gene value, contemporary participation 75. And the easiest way I can build a search engine on top of this data is to calculate some kind of distance between two works. And then we can use Euclidean distance, cosine similarity to do that. And once I have this distance, I could just sort these works by that distance and get myself a result, right? And that's actually quite simple. Unfortunately, we're Russian developers, so we can't do this. We can't do anything simple. And how many Russian developers are here? Yes. So, love reinventing the wheel and making things way more complicated. So we set ourselves off on building a search engine for millions and millions of works, despite the fact that we only had maybe 5, and we had to beg a gallery to give us the 6th. And we started by thinking about storage. So how do you store this data? Well, of course, you put it in a SQL database, because SQL databases are better than non-SQL databases. And you start with MySQL. It's very, very typical. And you create a table for artworks. You create a table for genes. And then you create a table for gene values for a given artwork. So you can imagine how many rows you have for something like this. It has some disadvantages. One is that If you're going to build a nearest neighbor in SQL, okay, I'm going to do Euclidean distance between every artwork with every other artwork in SQL is going to be a little slow. So to solve this problem, I will try to preload all that data at runtime. So when the service starts, and now it takes 20 minutes to start because I have to do a join for every single genome to get it out into memory. So that's not going to work. And we spend a lot of time trying to optimize that. And of course, we can optimize it down to, the 2-3 seconds query, and that's web acceptable, right? I suppose. All right, that doesn't work at all, but took a long time and was quite painful. So try to find better solutions. MongoDB is the solution to all your problems 5 years ago. Well, actually, it's kind of cool because the document that you store inside for a given artwork, like my flowers artwork, you can just put the genome as is because the keys are strings and the values are numbers. That's what I want. It's a dictionary. It's a hash. There are some small problems with that, notably that I'm using a lot of space because all these keys are actually copied again and again. So for every artwork, I'm going to have a hash with contemporary participation in it. And the other problem is performance. You can't actually index on too many of these. So if I want to find everything that has contemporary participation, I can add an index, but there's a limit to how many of these keys you can have. But let's build, on top of that, let's build a search, and that's what we did. To get started, it's really simple. You already have the data in memory because MongoDB is effectively in memory, and you can just write a nearest neighbor in 5 lines of Ruby, and you're done, right? So I can build a prototype with this really fast, and that's what we did. It took a day to really build a prototype that was already way better than the MySQL version because we didn't need to do anything complicated. No preloading, nothing in memory. You just take MongoDB for each artwork, calculate the distance with every other artwork, produce some kind of output, and here you go. That's my search engine. And that's good enough to demonstrate this in front of a bunch of investors. It works great, and it's a good start. But as the data set grows, it becomes a problem because you can't do this real time. If you have anything more than 5 artworks in the system, iterating over the entire set of artworks and then calculating the distance with every single other artwork is not going to work. It's a good exact result, but not good enough for an actual website to do this. So we started opening math books, and that's something I recommend generally when you've been trying to brute force the problem. Open Google a little bit of papers, and you find some interesting algorithms to do nearest neighbor. The first one we tried was called locality sensitive hashing, and it's really clever. It hashes your data and then gives you a bucket, a partition. And then the property of these partitions is that the objects that you put inside have a high probability of being your nearest neighbors. So I have an artwork, I hash its genome, I get a bucket. I look in the bucket, and then I can do exact nearest neighbors in that bucket. And maybe I have 100 things in that bucket, and that's good enough. Now, the problem there, though, is that not all these items will be correct, so they won't be nearest neighbors necessarily. And then if I don't find enough items, I have to look at the nearest bucket. And I have to keep going like this. And so if I want 10 results for my work, then I don't know how many buckets I'm going to have to look and how many actual cosine similarity math iterations I'll have to make to find 10 results. So some queries are really fast, some queries are really slow. And the whole art in this is partitioning the buckets in the right way so you have more or less the right results. And then worse, there are some results that you'll never find because the hashing function will land them in the wrong place. And then you're stuck. So there are works you can actually never find in the system. That's not great. And we did it really, really simply. We tried to do it live on the system. Creating that index was too slow, so we started Mongo dumping all our data into S3 and then Mongo restoring it into another MongoDB instance and then doing this kind of math offline, producing an index as an output. All right, so that worked okay, and it was really fast, but with all these problems. So then we went back to Google and found a very interesting algorithm that's actually very simple. And it's a little longer, but it's called NN descent. And the way it works is it's really amazing. Imagine I wanted to find all the nearest neighbors in this room. I'm going to have you all hold hands, and then I'll compare the distance between me and the person I'm holding hands with, and between me and the person they're holding their hands with. And if my neighbor's neighbor is close, I'll just swap them. And then eventually this converges to the nearest neighbor graph, which is beautiful. So now I can do an exact nearest neighbor offline, and I can do it in a parallel way, and I can do it in an exact way. So I'm going to end up converging to a nearest neighbor graph, which is awesome. However, it takes a long time, and I have written a bunch of Ruby to do this. So that's cool. 5 years later, we find that there's this thing called Elasticsearch, and actually Elasticsearch now implements all the stuff out of the box. And it's really fast, and it's called More Like This. It's a package in Elasticsearch, and there's really no code to write. It's real time. You don't have to do anything offline. You just put the data there, and you make a very simple More Like This query, give it the fields that you want, and internally it actually uses a lot of the similar algorithms that go there. So I think it's a great story of how we wrote a lot of code, tried something complicated with storage, and then ended up with just using a piece of software that just does it out of the box, and there goes all our science efforts. Okay. So let's talk about general data processing. General data processing is something everybody does, right? You have some data, you want to process it, you want to output some other data. Some people tell wonderful stories. I was talking to an ad company. They take 20 terabytes of data a day, they run it through some kind of cluster, and they produce 10 gigabytes of data in output a day, and it looks super awesome. Now, ours is a little smaller and a little simpler, and so we thought, oh, we'll do it. We won't complicate our life. We'll just try to do this incrementally on top of our original Ruby apps. But MongoDB is, you can't run MapReduce inside the MongoDB in real time from the same instance that serves web traffic, for example. That's going to lock up a bunch of stuff. So, we Mongo export, Mongo import, and have this kind of mirror of data. And in that mirror, we're going to do work. And so we have this unwieldy cluster of EC2 instances that's doing work. We wrote a queuing system based on Rescue that would run this job. And then the problem is, how do I bring this data back and read from it at the same time? So we wrote a library called Mongoid Collection Snapshot. And basically, it's a way to version collections in MongoDB. So I will go do offline processing, copy the data slowly back, and then I can access the latest version of my snapshot. So it's very simple. Once the snapshot is committed, it becomes the active snapshot, and we delete the oldest one and keep 2 at any given time. It's quite useful for very, very simple things like that. And our jobs now, in the beginning, they run for 10 minutes, then they run for 20 minutes, then for 2 hours, then for 8 hours, and as the data grows, 24 hours, and now we have people complaining that they uploaded something, it's not actually visible in search for 2 days. That's a little slow. So we move forward, and after multiple iterations of homegrown software, settled on using Spark, and so that turned out to be quite awesome. We use the way it works is that we export data from all over the place to HDFS. And it's about, today it's relatively small. We have about 150 gigabytes of data. We do the same thing from our PostgreSQL databases, from our MySQL databases, all our stuff. Like different services now have their own databases. We're certainly no longer a big monolith of things. And so again, we dump all that to HDFS with Scoop. And now you can actually create a schema to look at that data, which is really nice. Now you have all your data available in one place, and then you even have your logs, so like daily requests or whatever else you want out there. And then we write workflows, and those workflows do the kind of operations that we used to do, such as creating indexes. And I'll give some examples later of what those indexes look like. And here's a typical workflow. And what's nice is that a lot of our jobs are similar and need some kind of preparation. So maybe I need to normalize some genome. Maybe I need to remove anything that has a certain set of values. So one typical thing would do TF-IDF on a genome term frequency by inverse document frequency. It's basically if I need to figure out, I have a genome with 60 genes, and I want to find out which genes are actually relevant for this work. So I'll compare the frequency of the genes in that genome to the frequency of the genes maybe in the entire data set or of all the genomes for a given artist. So it's very similar to extracting content from a book. You just look at the frequency of words in this page versus the frequency of the same words in the entire English language, and you end up with the words that actually matter. Out of that. That algorithm needs to run, and we use the output of that in many, many different places. So now you can have workflows that have shared operations, and then those workflows will yield some kind of output into multiple places as well. So some of our suggestions now run in 23 minutes, and it used to run in something like a day and a half before in our homegrown system. The stuff is really fast. All right. The next one, that's again a very typical to do in a kind of a startup-y place as us. It's real-time analytics. So this came up in the previous talk where you start by doing, you throw in Google Analytics, you throw in Mixpanel, you do all kinds of spot analysis on that, and then you also might want to export some data via Ruby code, and then maybe you'll load it in some kind of SQL database, which you'll call a warehouse, and then we slapped Chartio on top of that and gave charts to people. And we wrote a ton of export-import code, just boilerplate, and that ended up being really hard to manage. So we iterated on that and made it a little bit simpler. So we said, okay, we're going to try and do this real time. So we picked Snowplow. So Snowplow has this concept of object, subject, verb. We tried to standardize all our events basically in that mode. And that was really, really difficult to do across all the projects because 10 developers have 10 different opinions. And it's kind of hard to do. And so we were one of the first to actually stream data from Snowplow. And Snowplow is a batch type operation usually, and so streaming data from Snowplow using AWS Kinesis has worked for us a bit, but it took a long time to build. And then finally you see data in Chartio, but now we have a workflow of this data. Then we threw everything out because it was getting crazy. And so today we send data to Segment. How many of you use Segment.io? There's not enough hands here. It's really awesome because you can send data there. It's basically infinite storage. And then you can turn on and off data coming out of it. So it's kind of sits like a buffer for you. And our purpose of this data coming from all over the place, client apps, server-side apps, and so on, once they're in Segment, we're going to try and move them into Redshift. And Redshift is our warehousing database where we can now do SQL, we can do all kinds of analysis, and we have Looker on top of that. So we have something about 930 gigabytes of data in Redshift today across 1,300 tables, and this is the truth about everything we're doing, and it's write only. We kind of add more data as things happen, and you can see them in Looker. And this is a real graph from Looker, and that has, I won't tell you what it is, but it has really enabled the entire team way beyond the engineering to analyze all data that we have in one place, create dashboards, write queries, and be able to really work with data. So we have sales team working with data and support teams working with data. And Looker is the thing where everybody sees what's going on. So I've shown you some stories around storage. Search, general data processing, and real-time analytics. And that's very typical life cycle of any project, of any startup, where you have to solve these problems, and you kind of iterate through them in difficult ways. So I wanted to give some examples of what we do with this, because I think they're interesting as good good data problems. So the first one is we want to suggest artworks to users, and this is old data. We have something like 700,000 users today, but we now can do these suggestions. We use approximate vector similarity. So we basically take the genome of a user of their favorites, and then we try to match it. We try to do distance with every single work we have in the system. And if you imagine my old system where I have to do this by hand or with some kind of LSH or with some other algorithm, I have to build this complete graph. Much simpler, and so that would take 4 hours to build. We just reused our search technology, but the inputs were different. Once we move this to Spark, you can simply do a MapReduce, kind of a dot product of these things, just find the overlaps. It's really good at doing that, and now we can do 700,000 users in 23 minutes, and the results are actually better. You're getting, with a lot simpler math, you're getting much better results. So these are my recommendations from a couple of days ago of what the system recommends for me, and you can see some Russian artists and other things in there. I don't know what that bloody photograph is doing in my recommendations. I have no comment on that. Okay, so another one that I really like is what is the likelihood that this art will sell? Now, that's a very interesting problem, because first you need quite a bit of data, quite a bit of data about sales, which we tend to have. And then what we did is we simply took all the features that we have, everything we know about the artworks, looked at the ones that we have that have sold, and trained a machine learning model to just do this. So this is something you can do on all kinds of data. You're trying to predict what the outcome will be. Just put a bunch of information in it, train it, see what the outcome will be, and score other artworks in that model. It turns out that it's a terrible predictor of the things that will sell. However, and it's a good example of how you constantly get new sales and realize that it's not a system, and you can't just go back and predict this kind of stuff, even though mathematically that seems like it would make total sense. Turns out, size of an artwork, it actually doesn't matter. So this is where the limits of machine learning come in place. But executing and experimenting with this is really easy if you have something like Spark set up, and you can just do this. It's very easy. Another one we try to do is infer prices for secondary market artists. Now, this one is fun because artwork prices are generally pulled out of thin air. The way galleries decide what something should be selling for is basically based on anecdotal evidence of how things have sold before. So if I'm willing to pay twice as much money for some work by some artist today, then the next price should be higher than that. It's pretty obvious. And then they grow and collapse the same way. It's not a science at all. So we just took the prices of the things we know. Oh, and it's really hard to actually obtain a price for a work. And the pricing is for you. It's not necessarily the pricing, like general pricing that you find on Amazon. So if I inquire on a work, if I am a known collector, the price will be a certain price. And if I'm not a known collector, the price will be very different. And then there are works that I just can't buy because nobody wants to sell them to me. So that's quite unusual. But pricing is the information that everybody wants before they even inquire on the work. And giving people an idea of how much something can be worth really matters and gives them the chance of actually going and doing the next step. So we think price transparency is really important, and eventually the galleries will all understand that just publishing more prices will sell more works. It's kind of not the case today. So we try to infer the pricing. If we know a bunch of prices from this work from all over the place, maybe we can fill in the blanks. And this is exactly what this does. And then it creates really pretty graphs and stuff like that. Mm-hmm.
In the end, you generate random numbers.
Yeah, it's random. Once we know that the prices within a certain range. Turns out those ranges are not that narrow, and so you have to pick something in between. And you just find a random number in between those. So we could totally pick the middle, the mean. Like, there's all kinds of other things. But we found that the even telling people what we think it's a price actually mattered more than the actual price. Because they're not actually purchasing the work just yet. So giving them a range is good enough. We think that value is of a certain amount was good enough. It didn't need to be too scientific, so I threw that in thank you for noticing. So that, the difference between theory and actual implementation sometimes is exactly that. In the end, we just put a semi-random number in the range out of there. No, well, so we do restrict it to some boundaries, and then we pick it out of thin air, just like galleries do, yes. So I think, what else this can be used for? You can use, you're doing all this data science, and it's really helpful with recruiting. So people really want to work at companies that do machine learning and that do AI and that do something really complicated. And so we're not like anybody different. The one thing that I would say is that in the end, a lot of these algorithms, as you can see, are pretty simple. And we learned very quickly that what really matters in the outcome here is the quality of the data. The moment where the Art Genome Project has really started working, and by the way, how do I know it's working? I take somebody who's worked in the art world for a long time, I put them in front of a computer and I say, click on a bunch of artworks, I'll show you similar works by other artists, tell me what you think. And they went from saying, this is terrible, I can't believe these things are together, to this is really awesome, I really think this is doing something magical. And the difference there was just data. So in the end, we ended up with very simple algorithms, and we ended up with paying a lot more attention to the quality of data and how people genome those works as opposed to the math that comes from there. All right. So a few conclusions before I go to questions about what we've learned over this time. Yes, beware of Russian developers. They will overcomplicate things. It is definitely a big learning from there. 5 years ago, 6 years ago, I would go into a project and really think about what kind of database do I need. Should I use MongoDB, which was the hot database? Should I use PostgreSQL? That seems like it's infinitely scalable these days. Should I use something else? And I think it's time to retire that thought process completely and really think about a service or high-level service. So we've used Compose for a lot of things. We use Elastico for our Elasticsearch. So we're now looking at these interface level things and not just about like which internal storage system is better than another. And I think 90% of your problems can be abstracted away at that level. So I recommend choosing a service these days and not a database. You want to get your data flow and warehousing in place right away. We should have done an end-to-end story of our data and how it flows from every single system into a data warehouse at the very end from the very beginning. It would have been really easy to do on day one. It was really hard to do once you already have data and you have to move it around. Sometimes I feel like we just were lazy and tried to make really incremental things, and they ended up costing a lot more. We should have done something like Segment and Redshift in the very early days. Now, those things didn't exist when we got started, and so that's a good other lesson. If you wait long enough, somebody will solve your problem for you. I think every single slide on this here is an example of that. Elasticsearch totally solved our nearest neighbor problem, like out of the box, that we spent 2 years building. And today, you think like, oh, how am I going to store a petabyte of data? Just wait 2 years, and the petabyte of data will be nothing. It's a good lesson. And once you have that flow, then you can build things on top of it. And so focus on kind of the high-level purposes of APIs. Maybe I'm just in management more these days, and I see things from a much higher level. But I really think we ought to think about what these data systems are producing, what questions they're answering, and who they're serving, as opposed to how we store it, how beautiful the algorithms are, or anything like that. So on that note, thank you, and I'll be happy to answer any questions in the back.
So the genome, you just said at the end, data matters. So were you using a content team to classify the genome?
So the question is, have we been using a content team to classify the genome? So yes, we have a team of art historians, and they do two things. They come up with new genes. So, for example, they started by looking at art movements. And young British artists was a very important art movement, so they created a gene called Young British Artists. And eventually, maybe there are too many works with a particular gene applied, and so they start splitting the gene in two and dividing the works in North American abstract expressionists, South American abstract expressionists, and things like that. So that's constantly evolving, and that's the team also that does the genome values as well. And it's a research project. It's kind of an amazing research project in art history that's not about the visual of the art, but really about art history.
So then how long does it take you to redo the entire database once they figure out that you need to split something?
Well, so it's an ongoing process, right? Because we use Elasticsearch now, they basically recreate genes. We have workflow that will rename things around there. So they just modify data in place, and then we apply the changes and replicate them into Elasticsearch. And then it just does the nearest neighbor problem in a straightforward way for us. Yeah, so what if you create new genes? So note, in Elasticsearch, this is query-based, right? So you just say the things that matter to me are genes, and it will actually look at the data and reorganize its indexes and rebuild the picture again and again. So internally, from what I understand, and I haven't looked in depth in the code, it just constantly rebuilds the nearest neighbor graph based on your data.
You need one person to look at each artwork and say, is gene here or not?
Yeah, so a person needs to look at every artwork to change the gene values. So yes, it is a manual process, and it's hundreds of thousands of works. We obviously have tools. So for example, you can we wrote a whole app for this called Helix, where you can say, show me the works with this gene value or this genome. And so they take it as projects, and it's the materialized version of their research, where they will describe a new gene, imagine how you could apply it, learn from each other, and then distribute the work across the team. I think it's about 10 or 12 people now that just full-time edit data in a massive Excel-like UI written in React and all that cool stuff. So it's fascinating. I think for an art historian, it's the best job ever, because you are actually doing art history research, and most art historians don't, unfortunately, have the pleasure of working with art or art history. We get some like 600 resumes for every opening on that team. It's cool. Most art historians just have to end up doing something else in life, like becoming programmers. I think we love hiring career changers, and I always encourage people who have not found their calling in a particular field to try something else. And we do have, I think more MFAs than computer science degrees on our engineering team. That's just normal. We like it. We like it this way. Sorry, say it again? Programmers as art historians. I think I will never know enough about art history to be a really good art historian, but most people go the other way these days. But it's a fascinating subject. Please go.
I think you mentioned at one point when a user uploads an artwork. So do you take just submissions from the general public, or is this just like recognized works that come by?
Yeah, so not at all. We don't take submissions from the general public. We work with galleries, institutions. We have something like 4,000 galleries on the site, 600 museums and institutions, including the largest ones like the Whitney Museum in New York or the Guggenheim Foundation, the Louvre, and others. So these works come from professionals, if you want. We don't work with artists directly either. Yeah. Excellent. Yeah, we should talk. I think DeviantArt is an awesome site. Yes, go ahead.
So I had on one of your slides that had segment, redshift, and looker. Segment fed into redshift.
Yes.
And you were saying you were using Lambda for stuff. What was going
We tried to use Lambda for a while as like there's data and we want to push it to Redshift, but now Segment has a connector, a piece of software that can automate that for you from.
If you were using it for like doing transforms of the data?
Yeah, most of data science problems are have nothing to do with science, and it's all about moving data around. So if you are your job as a data scientist, you're like, oh, I need my data over here so I can do something on it. So you spend all your time writing connectors and plugins and all that. It's a really hard problem to solve. Yeah, so that was just like an implementation detail for how that data is moved. Thank you. If you have more questions, just find me after this at lunch. Thank you.